So electromagnetism, what it is? Well, it's the production of a magnetic field when a current flowing through a conductor, according to the laws, basic Ampere's law. Many types of useful devices such as tape recorders, electric motors, speakers, solenoids, and relays are based on electromagnetism. Basically, it is the invisible lines or forces of the magnetic field form a concentric circle pattern around the conductor and are continuous along its path. The concept of the magnetic field was basically invisible lines, and Weber managed to calculate the number of invisible lines, which is 10 to the power 8 lines is equals to 1 Weber. So this gives a unit of magnetic field or magnetic flux as Webers. WB is a short form for it. Magnetomotive force, which is pretty much similar to our potential difference electromotive force, or the thing which we are very much familiar with is the voltage. Now, of course, the magnetism and electrical circuits both are interconnected and both are actually the same. The reason we are using a different words because it helps us to understand the construction of the transformers and mutual induction, and to be able to predict and calculate the losses, etc. So the first term or second term now is the MMF, magnetomotive force. And what it is? Well, it's like a voltage, but as we know that the current flow through a conductor produces the magnetic field, what produces the magnetic field? It's the force that produces the magnetic field. So we have a terminology for it. It's the MMF, magnetomotive force, and is proportional to the current flow through the conductor and the number of turns of a coil in a piece of material. The unit of MMF that turns out to be is ampere turns, or capital A, small t. Well, of course, there are a number of applications of a simple device that has a coil wound on a piece of material, and we call it a solenoid, where we want to achieve a linear motion or vertical motion, where the solenoid has a perfect example that can be applied, for example, on automatic door locking systems for electrical or any vehicles. So what the concept is that the solenoid is an artificial electromagnet. So you purchase, for example, a neodymium magnet. Each and every magnet has a north and the south poles. Now, it is possible to achieve that magnet by just having a coil and the current flow through it. And that's the perfect example of an artificial electromagnet. And applications are pretty much everywhere in the stator of three-phase induction motors, single-phase induction motors, generators, transformers, and all of the electromagnetic devices. And it is possible to find out the polarity of the north pole, or the polarity where the field actually passes from the north to the south. And it can be done using Ampere's right-hand solenoid rule, where the thumb points towards the north pole, and if we know the direction of the flow of DC current, then it is possible to find out the north pole. Now, of course, we are dealing with the alternative currents, but to understand the behavior of the solenoid and the electromagnet, we started with the concept of DC current before we jump on to the alternative current. Because in the alternative currents, your north and south pole changes after every half of the cycle. So that's something to look after for. But what we are doing right now is just do the steady state calculations for the MMF and to predict the direction of the north and south poles by applying a pure DC current. So MMF is again plays a significant part, which is dependent on number of turns of a coil and the amount of current that it flows through the conductor. An example question that we went through, a magnetic flux of 50 microwebers or 50 into 10 to the power minus 6 Weber is set up in a magnetic circuit with a total reluctance of 2.5 into 10 to the power 6 ampere turns per Weber. Now the question says calculate the magnitude of the MMF. Now of course we haven't started, or we just covered the concept of reluctance in last week, week 7, but not in this tutorial, which is a separate topic that I want to discuss before doing this example question. So what is reluctance? Is the word that we use mostly every day. That means basically the restriction or to avoidance of doing something. It's more like a resistance in electrical circuit. But electromagnetic, from the electromagnetic perspective, the reluctance is the opposition. When a current flows through a conductor, it produces the magnetic field. The opposition to the establishment of the magnetic field in a particular material is called reluctance in the magnetic circuit's perspective. And the value of the reluctance is directly proportional to the length of the magnetic path of the material and inversely proportional to the permeability and to the cross-sectional area of the material. Now I mentioned the word permeability, which is very important to understand before we start the standard construction of a transformer. So, reluctance unit is ampere turns per Weber. We will look at the standard magnetic circuit formula, which is very much relevant to the electric circuit Ohm's law formula. But what is permeability then? The permeability is each and every material, like the iron or stainless steel, has an ability to produce the magnetic field when a current flows through it. And the iron material actually stores the magnetism in its magnetic domains, and that creates the opposition to the flow of current in a magnetic circuit. So what we define permeability, how easy it is for a material to establish the magnetic field and how easy it for a material to collapse its magnetic field without storing or least storage of the magnetism. So permeability is an important parameter we always look at in the hysteresis losses of a transformer. So it's important to know the term permeability. And it is also significantly important to know that the higher the permeability of a material, lesser the losses in the transformer there will be. So that's important. Reluctance is basically dependent on the length of the material, the permeability of the material, and the cross-sectional area, and can be simplified as S is equal to L over mu times A. Mu is a Greek letter again that represents the absolute permeability. Now here I actually summarize the standard magnetic circuit Ohm's law. As we know, V is equal to IR. V here in the magnetic circuit can be represented to MMF, which is ampere turns, and the current basically can be represented as magnetic flux in Webers, and the resistance can be represented as reluctance in ampere turns per Weber. This gives us a formula, is equivalent formula as MMF is equals to phi times S. Phi is again the Greek letter that represents the magnetic flux. Again, these are all the same thing. The electric circuits, the magnetic circuits, both are the same thing. It's just the way we try to understand from the magnetic perspective of a same electrical circuit, or sometimes to understand the same circuit from the electrical perspective. But they are all interconnected to it. What is magnetic flux density? If you were to purchase any magnet from the market, then they normally provide a data sheet, and in the data sheet it usually says, you know, how many Tesla value it has, how many magnetic flux density it has. So the magnetic flux density, how much magnetic flux it has in a per unit of area in meters square. So flux per unit area is the magnetic flux density. Higher the magnetic flux density, better the magnet it has. There are other units for it, which is again Weber per meter square, or flux per area, which is Weber per meter square. In the CGS system, centigram seconds unit, it can be represented as a Gauss, as a unit for magnetic flux density, which is 1 Tesla is equals to 10 to the power 4 Gauss. The SI unit for magnetic flux density is Tesla. And the simple possible example is that if you have a single piece of coil wound on a piece of material, and that has a particular cross-sectional area, cut-through area, and the flux density would be dependent on that cross-sectional area, which means higher the cross-sectional area, lesser the magnetic flux density, and vice versa. Example question on magnetic flux density, again, is very straightforward. The MMF, magnetomotive force, produced by a coil sets up a flux of 300 microweber in a solenoid in a core with a dimension of 50 millimeter by 50 millimeter. Calculate the magnetic flux density. Now you already know that all of the units we have to convert into SI units. So if it's a millimeter, we have to convert into meter. If it's a millimeter square, we have to convert into meter square. So the formula is nothing, is a concept. So B is equals to B, which can be represented as the magnetic flux density, is equals to phi over A. And as you can see, is flux is 300 microwebers into 10 to the power -6 divided by 50 millimeter by 50 millimeter. So you have to convert 50 times into 10 to the power -3, which is 0.05 times 0.05, and this gives us a Tesla value of 0.12 Tesla. Another example question that we have is related to combine the formulas or the methods of MMF, magnetic flux density, and the reluctance. So a coil of 5,000 turns is wound on a core of a cross section